Okay, so welcome everybody to today's Strachey lecture. So these are termly distinguished lectures, which are named after Christopher Strachey, who founded the programming research group here. And this is a particularly exciting lecture because we've got two lectures, both Leah de Moura and Kevin Buzzard. And in my opinion, talking about, in my opinion, the most interesting thing that's been happening in computer science and maths intersection, maybe even union, in the last years. So we're really happy. I'm very, very happy to have them here. So before I introduce the speakers, I want to thank Oxford Asset Management, who's been funding the series since 2015. And we're really grateful for their support because we get such amazing speakers, thanks to them. And if there are any students and researchers that want to find out more about their company, you can do that after the second talk out of the coffee. So the way we're going to do it is we're going to have Leo's talk first for about 45 minutes. Then we're going to have questions and answers, and there'll be a microphone going around. And then we'll have the same thing for Kevin. Okay, so I'm really, really happy to introduce Leah de Moura, who is the chief architect of the Lean Theorem Prover, which we're going to hear about. He's currently, I can read it off, a senior principal applied scientist at AWS. And before that, he had a similar role at Microsoft. Now, actually, he's not only the person who built the Lean Theorem Prover, but actually lots of other theorem provers too. And I've got here a list of prizes for such work. So he received the CAV Award in 2021 for pioneering contributions to the foundations of the theory and practice of satisfiability, modular theories. The Haifa Verification Conference Award in 2010 for the most influential work in the last 5 years in verification. The Herbrand Award for distinguished contributions to automated reasoning, that was in 2019. The Programming Languages Software Award of the ACM in 2015 for the Z3 theorem prover, so that's another theorem prover. And we're really happy today to have him speaking to us about formalizing the future and Lean's impact on mathematics, programming, and AI. So thank you, Leah.
Thank you for such a kind introduction. Thank you very much. Very happy to be here, and it's a pleasure to be here giving a talk with Kevin today. I want to tell you about Lean. The original motivation for Lean was in software verification, right? I mean, Z3 was very popular at bug finding at Microsoft, was very influential there. But Lean, the goal was, can we have the same success of software verification? We went to a very strange path, having impact in mathematics that we never dreamed of. But the goal in both cases is like, in both software, mathematics, and AI, today we rely on manual review, partial testing. A mistake in a theorem can be catastrophic, invalidates the whole results. Same thing for a critical piece of software, right? And one thing I see all the time, people fearing to make a change to a piece of software because they fear by making the change, they may be introducing a bug, especially if it's a critical piece of software. In Lean, you have machine-checkable proofs, right? You don't need to check them only with Lean, but with also external checkers, and this completely avoids the guesswork, right? You create trust. You have absolute trust now that your result is correct. And there are many consequences that we didn't expect. Like, it's not just about proving, but about collaboration. And that's one of the messages we want to communicate today. Lean is an open source programming language and proof assistant, right? We couldn't dream the impact he's having in mathematics, software verification, and AI. The project started in 2013, right? The goal at the time was to combine the automated interactive worlds. They are both called Z3 and Lean are both called team improvers, but they are completely different beasts, right? And the main thing is the machine-checkable proofs. We say that it eliminates the trust bottleneck, not the trust between humans, but now the trust between humans and machines, AIs, right? And it opens up new possibilities for collaboration. Let's see an example here how Lean looks like. This is Visual Studio Code. I think the community, this is the favorite editor used by the community. You can use Vim, you can use Emacs, but VS Code is the most used one. And here we have an example, very simple one. In Lean, you have libraries. Here we are importing mathlib, the Lean mathematical library. We have definitions. Definitions have names. It's called odds. Here, it's stating that n, a natural number, is an odd number if there is a k such that n equals 2 times k plus 1. Right? It's the usual definition. Now that you have a definition, you can write theorems about this definition. You can give names to theorems, like the name here is 5 is odds. And the claim is that 5 is an odd number. Right. After you made a claim, you can start trying to prove. This is a proof. You're saying that k is 2, and Lean accepts it as a valid proof because 5 is 2 times 2 plus 1. This is a proof that 5 is an odd number. If you give an invalid proof, Lean will complain. We are going to get a squiggly line. Now let's try to prove something more complicated to make a point that Lean is an interactive game. I was very happy. It's funny when Kevin told me this, that he started saying, "I don't want to offend you, but Lean is my favorite computer game." And I was actually super happy when I was a teenager. I loved to implement computer games. None of my games when I was a teenager were played by anybody but by myself. And now I finally built a game that had real users, right? And here, on the right-hand side, this is the board of the game. This is like when you're playing chess, you have this state of the chess board. Here, the right-hand side is the board game. Let's see. We are going to start the first move of this game is intro. We are trying to prove that if a number n is odd, the square is odd too. You're going to do an introduction. We are giving name. If n is an odd number, there is a k. We are giving a name, k1, to it. And we also give name to hypotheses in Lean. You are saying the hypothesis, because we know if for this k1, we know that n should be equal to 2 times k1 plus 1. And we give a name here, E1. We can give names to hypotheses. Then we use the most popular move in the game. If you go to mathlib, you're going to find thousands and thousands applications of this move. It's the simplifier. You are telling here Lean to apply simplification rules. It's telling also in the square brackets, use E1. Basically, you are telling Lean to replace n by 2 times k1 plus 1. You are also telling Lean to expand the definition of odd number. And Lean marks in green the part of the game board that has been modified. In this game board, it's very simple, right? It's just 3 lines. But a real one can have several pages long. And knowing which part of the game board has changed is valuable. Then we use the game move again. This is a standard way of proving existential in Lean. Again, we see the new states of the game boards. And we finish the game using the linear arith. This is like a powerful move. It's saying use linear arithmetic. Linear arithmetic here means you can apply associativity, commutativity, distributivity, all the usual rules. This is like a big move. It does many things behind the scenes. And you finish the game, Lean is telling you, you won. No goals to be solved anymore. And Lean is not just an interactive game. To many people, it's also an addictive game, right? I think this is one of Kevin's students. I mean, when Quanta Magazine wrote the first article about Lean, they interviewed many people from the Lean community. And I loved these quotes. She was saying that she could do 14 hours a day, never gets tired, feeling a high the whole day. I was really happy. I implemented a game that people are addicted to it. And MathLib, it's unbelievable now. It's a collaborative project. The library has contributions from more than 500 people and more than 1.8 million lines of code, right? And this is the article I was talking about in the previous slides. Another quote I love is from Heather Macbeth, because it really captures the spirits of the community. She's building something because she believes someone, this is the foundation for someone to build something bigger. And at the time felt like what you're going to build on top of MathLib, we couldn't imagine how many projects would have MathLib as the foundation, not just in maths, but also in computer science. I'm going to tell a story about mathematics, a few about software, and a very short one about AI. Kevin's going to tell you way more about AI during his talk. Let's focus on mathematics first. It's impossible to talk about Lean without talking about the perfectoid spaces projects that Kevin, Patrick Massot, and Johan Commelin did in 2019. This is the project that brought a lot of attention to the system because they formalized modern mathematics. They shown that Lean was not even capable of doing formal advanced mathematics, but also they learned that it's also a way to communicate. After you formalize a mathematical object in a computer, math is data. Data that can be processed, transformed, inspected in many different ways. For example, the graph, this dependency graph on the left-hand side was automatically generated. From the perfectoid spaces definition, Patrick Massot wrote a program that extracts all the dependencies and builds this dependency graph for us. Right? You can visualize the dependencies because math is data now. If you go to Math Overflow, the second most upvoted answer for the question, what are perfectoid spaces, is a link to the Lean definition. And the cool thing here is that perfectoid spaces are really complex mathematical objects. But now that they have been formalized, if you have the patience, you can understand. You can keep following the dependencies. For example, here you can see that it uses something called a Tate ring. I don't know what a Tate ring is. You can click and ask the system, show me the definition of Tate ring, and it will do it for you. Let's see how this works in practice. This is one file from MathLib, from ring theory. The first thing, you can click at anywhere in your proof. It will show you the state of the game board at that point, right? And the game board is not a static object, it's interactive. You can hover over, for example, M prime is going to say M prime is a submodule. It gives you information about the objects. You can jump to the definition of submodule, right? Lean will show you the definition. And you can keep doing that. You can ask, what is an additive submonoid? It will show you the definition. You can keep zooming in until you are back to the axioms of mathematics. Right? You can see objects, you can change the definitions and see the impacts when you change. It's an interactive object now. Then after the success of the perfectoid spaces came the challenge from Peter Schulze. He is the person that came up with this concept. He said, okay, you have my definition. Now I have these results that I'm unsure about the correctness. I didn't publish it because I'm not sure. I challenge you to formalize it. And at the time he said, I'm going obsessed about this proof. I remember Kevin approached me saying, we are going to do it. We don't know how long it's going to take, but we are going to do it anyway. At the time, it felt like 2 years. Maybe it would take 2 years to do it. But in a few months, the main critical result that shows it was unsure about has been formalized by a group of people led by Johan Commelin. The cool thing is like people working together with the assistance of a computer, right, could do it. And Strachey was very pleased. Many small mistakes were caught during the process. The result appeared on Nature. And it's really unusual for maths to show up on Nature, on the Nature magazine. And didn't stop there. In my point of view, what was really unbelievable is that they did not only formalize the results, they also managed to simplify the proof without fully understanding the proof, because there was a computer assistance there. Johan was telling me that he could see only 2 moves ahead in this game. Basically, without being able to see the game board, you would not be able to do it. Lean was serving as a guide to them. Right? And this quote from Peter Strachey, I think was one of the happiest days of my life. When I read, I even asked, did Peter really wrote that? Kevin said, yes, it was Peter that wrote that, saying that Lean was really an assistant. Through the thick jungle, the proof is, right? And he couldn't keep all the objects in his memory, in his mind, right? And having computer assistance allowed him go beyond his cognitive abilities. So allowed people to simplify a proof without fully understanding it. I think this was really remarkable. This was only the beginning. There are many other projects using Lean. Kevin will tell you about the Formalizing theorem project today, that the Carlson projects run by Floris van Doorn. Also a big deal. There was the equational theorems project by Terence Stahl that was completed already. But I want to tell you about a new experiments that we have done a few weeks ago. Kim Morrison has been, they started using Lean like 10 years ago, right? He was one of the first users, right? I remember when Kim started using Lean, they told me, oh, I want to formalize quantum computing, right? They were working with the quantum computing team, and they wanted to formalize quantum. And many years later, now we are colleagues, we work together, and we finally managed to verify many results from a paper Kim wrote about quantum algebras, right? This is one of them, right? It's fully automatic, right? With one move, I'm showing you a new move called grind plus ring. You can do this computation automatically in milliseconds, right? This is not a toy, right? This encodes real algebraic constraints. How real algebraic constraints derive from relations among diagrams in a pivotal tensor category, right? And everything in milliseconds. The main point here is that we are Lean now. You can explore new mathematical and physical structures from topological quantum fields to fusion categories, right? Everything automatic. You don't need to do these calculations by hand. This is another example from the paper. You see the conclusion is a polynomial of degree 16. Imagine doing these calculations by hand. Or the one option is doing by hand, the other option is using an unverified computer algebra, and it feels always uneasy to publish a paper when you use an unverified system to check the results. And grind plus ring is just another move in the game, right? We're talking about all these moves in this game, but should we trust? I just mentioned that computer algebra systems are unverified, but what about Lean? Lean is a vast piece of software, right? It has many bugs, but Lean can have bugs, the moves can have bugs, but the kernel, it's small, it's the one that checks the proofs, the certificates that are created by these game moves that I have been showing you. But then you can say, well, the kernel is small, but it may still have bugs. Yes, this is right. The kernel has, sometimes we find bugs in the kernel. But you can export your proofs, right? And you can use external checkers, right? You can use external checkers to validate any proof constructed using Lean. You can inspect, remember, math is data now. You can inspect, you can even implement your own checker if you want absolute assurance. We never found a bug where all external checkers would say, yes, it has been verified. It's very unlikely that all verifiers, all external checkers have the same bug, right? This gives you a lot of assurance. What did we learn, right? We learned that machine-checkable proofs enable a new level of collaboration. Many people that worked on these projects, these liquid tensor experiments, they never met, right? Imagine working, usually in mathematics, you work with a small team, 2, 3 people that know each other really well. Here you have people working together that they never met, right? It's the power of the community. People managed to formalize the results very quickly because it was a bunch of people working together. You had an architect, like Johan set up all the interfaces, all the holes that need to be filled, but now people could work concurrently filling these holes, right? You don't need to trust the automation, the moves. People can add their own moves to the game. Lean is an extensible game, right? You don't need to trust the kernel will catch mistakes you made when you implement your own moves. And the final lesson is not just about proving, it's about understanding objects that are beyond your cognitive abilities, right? I think that's another big lesson we learned. Another thing is like, because math is data, we can do something that is done in computer science, in software development, automatic refactoring. I have this quote here from Zulip. Zulip is a channel where the community joins. It's like a forum where everybody exchanges messages. And it's very popular. Many members of the Lean community are there. And I love this quote from Ricardo Brasca, where he says that a result was automatically generalized. And he points out, imagine if it was an informal paper. Someone generalizes a result on a paper that was published 50 years ago. Who is going to make the propagate? Who is going to propagate this generalization to all papers that depend on these results? Nobody. But if math now has been formalized, this happens with a push of a button, right? Software. Lean now is used in many software verification projects, right? It is a programming language. You can write codes and you can verify it simultaneously. You don't need to use 2 different languages. You use the same system, right? You can prove that your code has the properties you expect. This code from Dijkstra captures this idea very precisely. Testing can only show the presence of bugs, not their absence, right? CIDR is a language at Amazon Web Services. It's a policy language. It specifies who can access resources, right? Users use this language, and they create a model of this language in Lean, right? The model is open source. Anybody can use the model, play with it. It's available online. How does it work? Basically, they have the actual implementation that's in production is written in Rust. And you have the model written in Lean, right? And they prove many properties about the model. And they run a battery of tests. They call differential testing. They want to check if the model and the actual implementation agree on every single input. If there is a discrepancy, there is a mismatch because there is a bug in the code or the model does not capture reality. And people have to go there and fix it. Why Lean was not used in production here? Right? It will happen one day. It does not happen today because, for example, for a service, CIDR is part of a service. There are people that have to be on call if there is an issue, to be able to fix the software, right? And today we do not have, Lean is not as popular as Rust. We don't have as many developers as Lean developers as Rust developers. But one day this will happen. If you want to learn more about Lean, you can see the blog post that my colleagues Kesha and Emina Torlak wrote about Cedar, how Lean was used. They were very pleased with the performance of the system. Another example is differential privacy. Differential privacy is a mathematical framework that ensures, let's walk back a little bit. Why people need that? Corporations want to collect data, but they want to respect your privacy when they do that. One technique they use is to add noise to the data, to make sure that nobody can figure out who this data is from. But if you add too much noise, the data is useless. If you add too little, sensitive information can leak, right? And in differential privacy, you are going to have pieces of software like a discrete Gaussian sampler, right? Used to calibrate the noise, the amount of noise in the data. And this is a project led by Jean-Baptiste Tristan at AWS. It's an open source library. You can also see the Lean code for this library. And one thing that I found interesting is that he not only proved correct, the sampler correct, he found bugs in the original implementation. In the paper, the original implementation was based on, and he managed to make it twice as fast, right? And why he did manage that? Because he could implement optimizations without the fear of introducing bugs. And SampSert would not exist without MathLib. Right? SampSert relies heavily on MathLib. It uses concepts from Fourier analysis, number theory, topology. And I remember when Jean-Baptiste mentioned his project on the MathLib channel, people were shocked that MathLib was useful for software, right? And this is not an exception. This is not the only project that relies on MathLib. The next one from Microsoft, Aeneas, right, is used for verifying cryptography. Basically here the setup is slightly different. You have software engineers writing Rust code for the crypto. Aeneas is a tool that converts Rust into Lean. And they verify this, it's almost like it's extracting the model automatically from the Rust codes. And the proof engineers make sure the properties they want are valid in the code in this model that was automatically extracted. And this could only happen because of two main ingredients they claim. One is MathLib, right? All the number theory is essential for cryptography, is there available in MathLib. And the second thing, Lean is extensible. They could add their own moves to the game. And they're going to soon publish these results. This is very new. Aeneas, the tool also is open source. You can use Aeneas to translate Rust code into Lean and verify the Lean codes using the Lean proof assistance. Another example is the KLR, right? This is basically an implementation of the kernel functions, right? They give a precise semantics for the kernel functions in a machine learning kernel, right? And they also provide translation from common kernel languages implemented in Python into this one implemented in Lean, right? The code is open source. They manipulate bit vectors and fixed integers. He is just showing an example where they're decoding a bit vector size 64. This is a great segue for another move in our game, BV decides. This is a powerful move. BV decides is a verified bit blaster implemented by Henrik Boving. He's in the Lean Throw, the non-profit responsible for developing Lean now. It's based on a verified set checker by Josh Klum. He was my intern at Amazon in 2023. And also Siddharth and Alex from Cambridge contributed many results needed to prove that the bit blaster was correct. BV decides, basically, if you had a problem in Lean about bit vectors, it is going to use a verified bit blaster that converts this bit vector formula into a formula in propositional logic. Then we will invoke a set solver that's not verified, CAD-CAL. CAD-CAL will generate a certificate that's called the LRAT certificate. And we have a verified checker for this certificate. That is not uncommon to be, the certificate to be 100 megabytes long, right? Set solvers are extremely fast, right? If you run for a few minutes the set solver, the certificate is gigantic, right? And BV Decide can check with the verified checker. And here's an example of BV Decide in practice. Pop counts is a common function you find many hackers use. Is for counting the number of bits that are true in a bit vector, right? Very efficiently, without any loop. You just do these fancy operations with bit vectors on the left-hand side, right? And it will tell you how many bits X has, right? True bits. On the right, you have the specking Lean. That's it's just iterating, counting how many bits are one. It's the standard implementation. And now we have a theorem stating that the implementation of all these funky bit vector operations actually match the POP spec, right? You have the statement of the theorem, right, saying that the implementation matches the specification. How the proof goes through. Basically, we use the simplifier, right? The simplifier is going to open all these abstractions, it's going to unfold them, expand them. It's going to expand the specification, the pop count, the environment, the values, and so on, and then call BV Decides. And you can see the state of the game boards. Here, after simp, this is the state of the game board on the right-hand side. It's just a bit vector problem. It's a bunch of bit vector operations with shifts, bitwise ends, addition, subtraction. And now you can just call BV Decides and blast through it, right? It proves that instantaneously in this case. Since we talked about bit vectors, this one, BV Decide, is blasting, is reducing a bit vector problem into bits. But there are other strategies. Lean does not fix a specific strategy for a specific problem. For example, here you can exploit with grinds the same one we did quantum algebra. You can verify. Bit vectors form a commutative ring. You can use the ring solver to solve this problem, right? And it knows, for example, it knows that this ring, the ring of bit vectors of size 8, has characteristic 256. It knows 256 is 0 in this ring, right? That's why this property holds. So here is using a completely different strategy. Instead of blasting things into bits, it's using the algebraic structure that bit vector satisfies. And you can also use grind, for example, for proving that this function shift down preserves the size of the input array. This is a function used for heap sort. All the array access here have been verified by grinds. There's no, when Lean generates code for this function, there's no runtime check for the arrays. The indices, it knows they're all in bounds. For example, when you say a square bracket child, it knows child is less than the size of a. It was proved behind the scenes. And the code generator can use this fact to generate efficient codes. And the proof that this function shifts down preserves the size of the array is just a one-liner, right? Again, a move is a powerful move that finishes the game in one line. What did we learn, right? We learned that for software verification, in software development, you can code without fear, right? You can implement optimizations that should, before sometimes the person implementing or making the modification does not know all the assumptions that are needed for that to work. They know something, but they are not fully confident about the maths. And now you have a proof assistant to double check what you wrote. Powerful automation is essential. Lean has been used in many different applications, verified compilers, policy languages, cryptographic libraries, and so on. You can find all the projects in Reservoir. It's like a repository. It's like a crates.io for Rust, where all the packages that are open source for Lean are available there. You can browse them, search them. You know for each version of Lean, each package is compatible with. And if you want to learn more how Lean is used in software verification, you can also read this blog post I wrote for Amazon, how Lean is used for coding and in coding to math in both directions. AI, I will be very brief here in AI, because Kevin will tell you much more. I will just tell you the obvious, that large language models are amazing, but they hallucinate. It's great that for maths, you can check, you can use a system like Lean to check if the result produced by a large language model is correct or not. And this is essential, right? Imagine one day large language models start proving maths like the Formalizing theorem automatically. The proof, informal proofs, more than 200 pages long. Would you trust, I mean, the likelihood a large language model made a mistake in 200 pages is really high, but we can check now, right? Machine-checkable proofs are the antidote to hallucinations in AI. Here, but the other direction, we talked about how Lean can help AI, but AI can also help Lean, right? There are several groups that are building AI to predict the next move in the game, and even to complete the game. You say, try to help me, they will try to synthesize a proof for the whole game for you. Lean Dojo is a popular package. It's from Caltech. It's great because everything is open source. The model, the data sets, the code, everything is open, right? There are also projects by OpenAI and MetAI where they solved some Olympiad problems in 2002, 2022, and 2023. But the big news there was AlphaProof last year. AlphaProof is an AI built by DeepMind. They did something that many people in the community thought was impossible, to build a system that can get a silver medal in the IMO, right? It's weeks before they announced these results. People in the community were saying, oh, this is going to take years, it will never happen, it's impossible. But now DeepMind has AlphaProof that could do it, build Lean proofs, right? That's a machine-checkable, right? To give you absolute assurance about the correctness of the results. Well, the lessons here, I'm sure Kevin will have many more, but one big deal here is that machine-checkable proofs allow us to build AI that does not hallucinate, right? AI are getting better and better at understanding, explaining Lean codes. For example, Turnstile, when he learned Lean, he said that he had ChatGPT on his side. He was asking questions to ChatGPT and he learned Lean with the help of ChatGPT. You can give a big Lean file. It will explain you in natural language what the file does, right? It will help you. You can, if you ask about this, what this move does, it will give you a really good explanation. Now, in the future, for sure, we are going to have AI systems that can prove rather than guess. Before we wrap up, I want to emphasize that one thing that's, we talked a lot about machine-checkable proofs, but another ingredient that enables decentralized collaboration in Lean is the fact that Lean is extensible. It turns out that Lean is implemented in Lean itself. Lean is a programming language. You can make it your own, right? The mathematicians, the MathLib community, all the time they change things themselves. They add their own moves. they make modifications to the system, they add their own new syntax that's great for maths. And the main point is that even if you make a mistake in a move, it doesn't matter, the kernel will catch it. But making the system extensible, I think was really important. Before the fraud, this non-profit for Lean started in 2023, sorry. 10 years after we started the project. It would be impossible to get to 2023 if Lean was not extensible. There was no team, right, building Lean. And remember the linear riff tactic I mentioned at the beginning? Actually, this is a move that was implemented by the MathLib community. Is inside of MathLib this move. Was not implemented, I did not implement this move. Was implemented by their Lean users. It's inside of MathLib. BV decides and grinds, these moves were also implemented in Lean. You can see the code for Lean. You can see the code and say, oh, this doesn't do exactly what I want you to do more. You can modify it. Another thing is that Lean got very popular in AI because it's very easy to introspect inside of Lean. You can, I said math is data, okay. When you formalize in Lean, math becomes data that can be processed. But how do you access this data? You don't need any new programming language. You can use Lean itself to introspect inside of the data. You can write a Lean function that traverses your proof objects. The dependency graph was built this way. Kim Morrison, the same one of the quantum algebra example, wrote a tool for extracting data and is used by OpenAI, MetaAI to extract data from Lean for training. The same idea of introspecting Lean objects can be used to build animations. If you go to YouTube, search for proof animation in Lean, you're going to find many of these animations that were built using a tool by David Renshaw. Right? And even for the solutions that DeepMind found, for the IMO, they're animated using this tool. The Lean Flow is a non-profit that started in 2023. Has 19 members now. It would be impossible to run the Lean project without the support of this foundation. The mission is to improve the scalability, usability, documentation, improve automation, and reach self-sustainability in 5 years. We're really grateful for the support from the Simons Foundation, Sloan Foundation, Richard Birkin, and Alex Gurko. It would be impossible to do Lean without their support. There are too many users now asking too many things, and people that want to use Lean for teaching, they have a high bar on usability. They want to use with undergraduate students, high school students. There are people that want better manuals, people that want more scalability, people that want this, want that. Without a team, is impossible. These nonprofits also would not happen without convergent research. Convergent came up with a new concept called a FRO, a Focused Research Organization. They compare a FRO to something like the James Webb Telescope or CERN, a project that is too big for academia and not profitable for industry. There's no profitability path for the project. There are many projects like that. And Convergent wants to support this kind of project and help raising money and running the nonprofits. Right? Without that support, it's a lot of work. I didn't know before. It's a lot of work. It would be impossible without the help of convergent research. Lean Flow by the numbers. Before the Lean Flow, it would take a long time for each Lean release, right? Now, since the Flow started 2 years ago, almost 2 years ago, we had 19 releases, more than 4,000 pull requests with bug fixes, new features, performance improvements, and so on. All the roadmaps, our roadmaps are all publicly available. Since then, Lean appeared 3 times in the New York Times, Quanta Magazine several times, Scientific American, and so on. The growth of the project also accelerated. If you we can count easily the number of projects using Lean on GitHub. There are more than 4,000. And you can see the acceleration after the flow started. The number of downloads from the Visual Studio Code plugin. We have data, the Visual Studio Code's marketplace provides data, but the data starts in 2024. You can see there were more than 40,000 installations, new installations, not updates, since 2024. How can you contribute to the project? There are many different ways you can contribute. You can help building MathLib, right? You can join the Zulip channel where the community gathers. If you have questions about Lean, your question is going to be answered in minutes there. If you are interested in machine learning kernels, you can contribute to the KLR projects. If you want to participate in a big formalization project, maths project, you can contribute to the Fermat's theorem formalization project that Kevin is running. You can create your own new projects, right? And you'll be indexed automatically by Reservoir if you host it on GitHub. You can use Lean without installing anything. You can go to live.leanlang.org and you can start using Lean, playing with it, MathLib, everything in your browser. You can also support the nonprofits, not just by providing funding and partnerships, but also advocating for the project. It's super helpful for us. Advocacy is really important. I'm very happy to be here today. The message I want to communicate is that Lean is an efficient programming language and proof assistant. The MathLib community is changing how math is done. It's not just about proving, but going beyond your cognitive abilities. Right? In the future, you're going to have AI that will be an assistant to you. You're going to have big projects solving hard problems, working with people that you never met, and even AI, everybody working together. Right? Lean will track the details, right? Decentralized collaboration allows large teams to work together. Right? You don't need to take the result of someone on faith anymore. Thank you very much.